Hey guys, I hope you're all doing good. So far what we have actually done is we have looked at numerical discretization. I had mentioned that the whole idea is we basically take continuous form equations and we are converting it into algebraic form so that we can solve it using a computer. Okay, that is the central idea here. So to do numerical discretization, what we actually did is we employed Taylor series, right? Okay, and in Taylor series what we actually did is we took the domain, and then if you have to compute the first order derivative on the second order derivative, what we did is we wrote the Taylor series expansion. So if this is point x, and what we did is at x plus delta x, if we have to evaluate the function, we take the value at f of x, we employ Taylor series and get the answer. Now to calculate the first order and the second order approximations of the first derivative, we were able to do it by just some simple manipulation. Alright, so we came up with different schemes. For example, for df by dx, we came up with central differencing scheme, forward differencing scheme, and backward differencing scheme, right? And then I also talked a little bit about the concept of a stencil. Okay, let me just write it down here, a stencil. So the idea here is when we are computing the derivative at a given point, so let us say this is point I, when we are computing the derivative at this point in forward differencing scheme, we take the information from the point on the right hand side. And we said that this boundary is called as the stencil. More appropriate name is numerical stencil. And in case of central difference, the stencil is symmetric, meaning if you have to compute the derivative at this point, you take information from the neighboring points, I minus 1 point and I plus 1 point. And just to refresh your memory, the forward difference scheme is first order. So basically the truncation error is first order. And then the central difference scheme, CDS, the truncation error is second order. Okay. And the point we try to make is the more the number of points that we have, the higher the accuracy is going to be. So let us ask this question. Okay. So now let us try to answer this question. Say that we have to come up with an expression for the second order derivative. Okay, so we need to approximate this expression. Okay, so this is the actual derivative and this is the numerical derivative. Okay, now we want to approximate it, but when we approximate it, let us say that we desire a third order accuracy or a fourth order accuracy, or any order. Okay, so how do we do that? In fact, that is the logical way of going about discretization. You first think about the order of accuracy that you want, and then you try to derive the scheme accordingly. So in this video, what we are primarily going to be focusing on is a method called as Taylor's table or Taylor table. So with the Taylor table, we can come up with numerical schemes to meet a target accuracy. All right. So let us say that, let's take the same example, d square f by dx square. And let us say that I need to come up with a second order accurate approximation. And I need to do that by using points I plus 1 and I plus 2. Okay, so if I draw the stencil, what I'm trying to say here is to compute the second order derivative at I'm going to be using information from the right hand side, I plus 1 and I plus 2 points. So my stencil is no longer symmetric. In fact, it is skewed. Okay, So this is called as a skewed second order scheme. Okay, and to derive this we are going to be employing the Taylor's table method. So the first thing that we need to do is, all right, so we are going to say that d square f by dx square is equal to a times f of I plus b times f of I plus 1 and c times f of I plus 2. Alright, so if we are able to figure out a, b and c, then we will have a scheme that's second order accurate and is also skewed. So how do we do this? Okay, so the first thing we are going to do is we are going to expand, we are going to compute f of I plus 1 using Taylor series. So f of I plus 1 is going to be equal to f of I plus delta x by 1 factorial into f dash calculated at I. Okay, and we are going to add a few more terms here, delta x square by 2 factorial plus f double dash of I plus delta x cube by 3 factorial f triple dash of I. Okay, so the derivative, we're computing f of I plus 1 by taking the values at f of I. So basically we are using information in this point to compute the function at I plus 1 point. Okay, you need to remember that. So the next thing I'm going to do is I'm going to write this equation down here, and do not ask me why I'm doing this because it seems quite obvious, right? I'm just saying AFI is equal to AFI. So just be patient for a while and hopefully you will understand why I'm doing this. Similarly, let's do Fi plus 2. Okay, so this is going to be f of I plus, again we are computing Fi plus 2 by evaluating the functions and derivatives at the ith node. Okay, f of I plus, if we assume that this is delta x and this is also delta x, basically we are dealing with uniform grids, then I'm going to get 2 delta x by 1 factorial f dash of I plus delta x square, and what I'm going to do is I'm just going to add 2 here, so 2 delta x to whole square by 2 factorial multiplied by f double dash of I just noticed that I have a typo here, this should be multiplication, plus 3 times delta x whole cube by 3 factorial multiplied by f triple dash of I. Okay, and in our expression we are multiplying b times fi plus 1 and c times fi plus 2, so I need to make sure I do that. Okay, so d square f by dx square is equal to a times f of I plus b times f of I plus 1 plus c times f of I plus 2. So what is this going to be equal to? So let's just do some simplification here. So for example, if I'm multiplying b with f of I plus 1, I'm going to be multiplying this entire equation by b, and this entire equation is going to get multiplied by c, right? So what I'm going to be ending up with is b times f of I plus a times f of I plus c times f of I. Okay, so essentially what I'm doing is I'm taking this term and this term and I'm just writing it down here. Okay, and then what I'm going to do is I'm going to add delta x by 1 factorial f dash of I plus 2 delta x by 1 factorial f dash of I. Again, it's going to be extremely useful if you're actually writing these equations along with me. Okay, so now what I've done is I've taken this term and this term. All right. So we still have a few more terms. So, and again, it's very important to do this. So I forgot to multiply. So this should be multiplied by B and this should be multiplied by C. And then if I take this term right here, I'm going to have B times delta x square by 2 f double dash of I plus C times 4 delta x square by 2 f double dash of I. Okay, hopefully at this point you are seeing what I'm doing. And finally, I'm going to have B times delta x cube by 6 f double dash of f triple dash of I, sorry, plus C times 3 cube is 27, 27 by 6 delta x cube f triple dash of I. Okay, so let's do a little bit of arrangement here and hopefully you will start seeing an important pattern. So I'm going to get A plus B plus C multiplied by f of I plus, if I take f dash of I as common, I'm going to get B times delta x divided by 1 plus C times 2 delta x. And then f double dash of I is going to get multiplied with B delta x square by 2 plus C 4 delta x square by 2. And similarly, for our last term, we are going to get f triple dash of I, and this is going to get multiplied by B times delta x cube by 6 plus C times 27 by 6 delta x cube. Okay, so this right here, if you take a look at the right hand side and then if you take a look at our left hand side, okay, so let me just write down my left hand side. So my left hand side is going to be an approximation for the second order derivative. All right, so if I'm trying to calculate dou square f by dou x square, then should I have the term f of I and f dash of I? I should not have, right? So in other words, this entire term, maybe I'll try to draw a box around it. Should be equal to 0. Okay, and if that needs to be 0, we are saying that A plus B plus C is equal to 0. Similarly, what about this term, right? Well, this term needs to be 0 as well because this is f dash of I and we are trying to compute d square f by dx square. So we are going to have b delta x plus 2c delta x equal to 0. Now let's think about this term. This is the term that we want, right? So if this needs to be approximated to this, then this coefficient, it has to be equal to 1, correct? Think about that for a second. If you don't understand, get in touch with me and I can explain it to you again. So I will have b delta x square by 2 plus, I'm just going to simplify this a little bit, 2c delta x square equal to 1. Okay, so I can do the same thing for this guy, right? I can say that this coefficient is equal to 0, but the problem is, we already have 3 equations and 3 unknowns, right? A, B and C are unknowns and we have 3 equations. So we don't have to worry about this equation and we just ignore it completely. And then let us try to solve this equation. Okay, so I can say that b times delta x equal to minus 2c delta x. All right, delta x is going to get cancelled. B is equal to, or basically minus b by 2 is equal to c. All right, so this is one simplification that we have. And then we can take this equation and substitute it in equation number 1. So I'm going to call this as 1, 2 and 3. And let's call this as 4. So let's take equation 4 and substitute in equation 1. I'm going to have a plus b minus b by 2 equal to 0. So this means a plus b by 2 is equal to 0, which means a equal to minus b by 2. Alright, so we have this equation. Alright, so b delta x square by 2 plus 2c delta x square equal to 1. And we know that c is equal to minus b by 2. So I'm going to have b times delta x square by 2 plus 2 times minus b by 2 delta x square equal to 1. So this 2 is going to get cancelled. So I'm going to have b delta x square by 2 minus b delta x square equal to 1. So I can take b common out. So I'll have delta x square minus 2 delta x square divided by 2 equal to 1. So b is going to be equal to 2 by delta x square 1 minus 2. Alright. So this is going to be equal to minus 2 by delta x square. Okay, I hope the math is correct. If there is anything wrong, just feel free to point out to me. So c is going to be equal to minus b by 2. So that's going to be minus half times minus 2 by delta x square. So this is going to get cancelled. So c is going to be 1 by delta x square. Alright, so which means we finally have a, and we know that a is equal to minus b by 2. So that's going to be minus half times, what is the value for b? B is minus 2 by delta x square. We are going to get 1 by delta x square. So a is equal to 1 by delta x square. B is going to be equal to minus 2 by delta x square. And finally c is going to be 1 by delta x square. So d square f by dx square is going to be a times f of I, right? So f of I divided by delta x square minus 2 by delta x square times f of I plus 1 plus 1 by delta x square multiplied by f of I plus 2. Alright, so this is how I would come up with a second order accurate method. Alright, hopefully the entire process was clear. The reason why this is called as a Taylor table method is because you can actually take whatever we have done so far and represent it using a table. So the idea is, okay, say that you have to come up with an approximation where you're using f of I plus 1 and f of I plus 2. Okay, so when you are coming up with these approximations, you are anyway going to be having the f of I term, and you're going to have f dash of I term, f double dash of I, f triple dash of I, and so on. Okay, so these are the terms that occurs in the Taylor series, correct? So all you need to do is, when you're trying to do a times f of I, b times f of I plus 1 and c times f of I plus 2, you just fill the coefficients. Alright, so here you would get 1, 0, 0 and 0. Oh, sorry, actually you would get a, and then here you would get b times f of I plus delta x by 1 factorial. So I'll just have it as delta x square by 2 and delta x cube by 6. Similarly, for the I plus 2 term, I'm going to have c here, okay, and I forgot multiplying everything with b. And for the third term, I'm going to have a coefficient of c times 2 delta x, c times 4 delta x square by 2 factorial, and c times 8 delta x cube by 6. Okay, and then what you can do is you can then just sum them up, and then you can just say that, okay, you know, a plus b plus c is going to get multiplied with f of I. This needs to be 0, this needs to be 0, and this needs to be 1. Alright, so that is how we derive the equations, and this is what is called as Taylor's stable method. So in the future, if you have to derive a 4th order approximation or a 5th order approximation, you put your stencil here. Okay, so this is where your stencil goes, this is where the Taylor series terms goes, and then you finally just sum it up and you basically say what that coefficient is going to be equal to. So I hope that makes sense, and I'll see you guys in the next video. Bye.